Good morning, ladies and gentlemen. My name's George Emsden. Talking of taking up John's point about the BAA, in the 80s I was a member of the variable star group for a while. So these days I'm retired financial advisor, doing, as my children are all grown up and I've got grandchildren, now George can do what he's really interested in, study radio astronomy, to which end I'm doing an open university degree in maths and physics. I have to say I'm not very good at maths, but I sort of get there. Secondly, may I thank John for giving me the opportunity to give a talk on an area of radio astronomy where I think I could actually add something. I mean, for example, I've always been interested in SETI. I've ran SETI at home on my computer since 1999, but with the billions of dollars and postdocs and professors and Nobel Prize winners now going into SETI, I sort of scratch my head and think to myself, well, what can I actually contribute to it? And sadly, I have to say, well, probably not very much. And the reason I've chosen this subject is that it is a neglected area of radio astronomy research. Now, we got Norman this afternoon talking about Schumann resonance and stuff like that. There's a very clear boundary between Norman's talk, because Norman's talk is what happens inside the ionosphere, whereas what I'm interested in is what happens outside the ionosphere. The reason for that is that at very short wavelengths, which we're not interested in today, and then at long wavelengths where from 10 meters onwards, the atmosphere or ionosphere starts to get opaque, and this is an area of astronomy which I think it would be useful to fill the gap. Now, I came across this book, and Norman's got some, a very interesting book. Norman's got copies if you're interested in Radio Nature by Ronaldo Romero, very interesting book. I came across this book back in 2012 when I did my radio amateur license, and I thought it would be useful to clarify some of the terminology today, which is copied from page 16 of this book. At the lowest end, you've got the super low frequency wavelengths of 100,000 kilometers plus, which is you get to geomagnetic, mainly geomagnetic stuff. Then going up by for the frequency by a factor of 10, 3 to 30 hertz. You've got Schumann resonance, brain electrical activity, precursors of seismic, of earthquakes and so on, and military tests. Going up again by a factor of 10, you've got extremely low frequencies where you have natural radio signals, submarine communications. I'll be doing a short aside on that in a minute. The harmonics from electricity supply networks. Then going up slightly, voice frequency, which we're all using now. And then into the terminology I use, very low frequency, which are natural radio signals and military communications. Going up the frequency table again, these are basically broadcast, long wave, medium wave, and shorter wave broadcasts. And as I said, the practical limit for radio astronomy from the Earth's surface is, well, that's actually a typo, it's 10 to 30 meters is the practical limit, because the ionosphere is opaque. I said I would mention submarine communications. The Americans came up with the idea back in the 50s or 60s of using very, very low frequency submarine communications, for the simple reason that at such low frequencies they can't be blocked. Now, the location for the transmitters was decided purely by the geology. There are about 12 sites in the States. For this sort of transmitter to work, the ground had to be impermeable, which in practical purposes meant granite, and of the 12, 13 sites in the United States, only Texas and here in Wisconsin were actually looked at. There was loads of opposition to this from the outset, people worried about their TV sets and electricity light supply being interrupted. So a cut-down version, Project ELF, was operational in 1989. It was a 14-mile antenna between two sites with a combined transmitter power of 2.6 megawatts. So two transmitters at the end of a 14-mile antenna buried in the ground. Of course, these had to be synchronized, otherwise you're going to get destructive interference. 2.6 megawatts at the output from the transmitter. Would anybody like to guess what the radiated power was from the antenna?
Less.
It's so much less I didn't even bother to calculate. It's 8 watts. You didn't even need the figures. And what happened, this is all just being absorbed by heat into the ground. I bought a book here off the internet, the whole story of this. 69 organizations vehemently opposed to this scheme. I mean, normally Americans are very patriotic, but a lot of people really didn't like this, engaged lawyers and everything. So eventually it was closed down in 2004, although the system is still used by the Russian and the Indian navies. I'm not just mentioning this as a curious side for this sort of frequency astronomy. Is also relevant to data, but bear with me, I'll come back to that later. So that's Project ELF. Now, if I'm going to stand here and say we ought to do let's do a survey of the very low frequency area in the sky, the first thing you need to do is go online and have a look and see what's been done already. This, I'm sure most of you recognize, is the Very Large Array in New Mexico. And the one that pops out most notably from July 2007, done at 4 meters wavelength. That's quite a notable one. More recently, there is LOFAR. Their idea of low frequency is a long way from mine, so just over a meter. This is centered in the Netherlands, but there's one branch at Chilbolton. There's this particular bit's in Sweden, I think, but it's like a starfish. The setup's rather like a starfish with very long curved arms. So that's the low frequency array. And I came across a Ukrainian radio telescope, which apparently will work at up to 37 meters when the atmosphere is opaque at 30 meters. I'm sort of wondering, why do they have it working at up to 37 meters? But anyway, that's what the data said. This is quite an impressive setup. It's a sort of T-shape on its side, and as a sort of summary, what's been done already at very low frequencies. This is a composite map done by Messrs. Kane and Ericsson from the University of Tasmania back in 2001. It's a composite from several sky surveys, but the detail is hardly very interesting because it's a resolution of 5 degrees, but this is more or less the best composite we can get at the moment. Regarding resolution, the previous slide, the resolution was 5 degrees. The very, very low frequency radio survey, the resolution was 80 arc seconds, an awful lot better. So, okay, George, this is all very interesting. Why bother? Well, the reason I'm bothering, no one seems to have done it yet. There's been quite a bit of planning done going back to the 80s, but no one's done it yet. It's an area of science where nobody's really done much work. regarding the whole radio spectrum, or electromagnetic spectrum. Now we got gamma ray telescopes, we got X-ray telescopes, all the way to infrared visible light, ultraviolet telescopes. We've got a super detail right from gamma, but this sort of fades out as you get near the lower frequency end of the spectrum. In my research, I came across some notes, and that's all they were. One of the Jupiter or Saturn probes did very basic probes about VLF frequencies, but I couldn't get any more detail on that. And just to make it all even more interesting, at the very low frequency end of the radio spectrum, by definition, the signals are very weak. And to cap it all, you got interstellar absorption as well. Now, when I started the research on this, I came across a paper by James Douglas and Harlan Smith, sadly no longer with us, so I couldn't get in touch. They wrote a paper, A Very Low Frequency Observatory on the Moon. This was, I've got it here, so five pages of pretty good stuff, and they suggested that it would be good for non-thermal radiation from the solar system, which would be, well, mainly Saturn, Jupiter, Earth, and of course the Sun. Synchrotron radiation from the Milky Way at wavelengths longer than 75 meters, plus away from the galactic plane, extragalactic radio sources. And as they said rather intriguingly, there's always the unexpected. Somebody said it was on the radio only a couple of days ago, in science, you very often find something that you would never even considered looking for. Now, this is when I was updating the slides, bit of homework 2 nights ago, I came across a more recent paper, much more detailed, and I pinched one of the pages off of this. It's a Harvard University paper. This is a very nice summary of the flux density, the frequency, flux density in a different way, so the sort of at different frequencies, and where, what sort of information you might get. It's also moved on from 1992 has moved on from 1985. Here, 7 years later, they're talking of a robotically deployed telescope, the one from 1985. They reckon 2 lunar rovers, 3 men. It would take a month to set up. Now this can be done in a day or something, and this is back in the 90s with an automatic, with a robotic lunar rover. This is from an Astronomical Society of the Pacific paper, and it has the ALPHA acronym, Astronomical Lunar Low Frequency Array, or ALPHA, and that is what they propose to, the area that they could reasonably research. What they reckon with this particular system is that they could, over a 12-year period, they could map 98% of the sky. So here we are at the frequency spectrum again. Now, the barrier, in other words, the difference between my talk and Norman's talk, is the ionosphere, and the question I asked myself, what sort of barrier is it? Is it a brick wall where absolutely there's no way you can see through it? Or is it perhaps something, perhaps like a chain link fence, where you can see through it? And I've got 1 or 2 ideas here. You can either do this from the Earth, or you can do it from space. So let me do this from Earth. Now, the headline says, zap the ionosphere. That isn't just something out of a Batman comic. That isn't so as outrageous as you think, because as I'll explain in a minute, this is more, we're halfway to doing this already. This particular picture is 422 watt lasers from a 50 centimeter projector aimed up at the ionosphere to create an artificial star. Also in July, in the Arabian Gulf, the US Navy have a brand new laser weapon system. This can now take down drones. I believe that's 50 centimeters as well, zapping the ionosphere. The laser beams aimed at a point in the ionosphere 90 kilometers up, right next to the area of sky that you want to look at. This creates an artificial star. It excites the sodium atoms, and what you do is you see how that light scintillates. You run it through the data as well, and hey ho! Instead of having a blob, you get to resolve it into two stars or whatever it is. This is an interesting example, a modern example of swords into plowshares. This is a direct result of the Strategic Defense Initiative, one of Ronald Reagan's pet projects. The idea of that was if there was an incoming nuclear warhead, you would identify it by laser. Oh, that's an enemy one, pow zap, no more warhead. That was the idea. It didn't work, but following the example of swords into plowshares, this is now used to take out the scintillation of caused by the atmosphere. So taking this one step further, I'm asking, this is a hypothesis, that's all, if we can create an artificial star, could we take that half a step further and create a window in the ionosphere? Now, I don't know if that would be a circle, a square, a long slit, or what the dimensions are, or anything. But if you could do this from Earth and create a window in the ionosphere, then it obviously, you could do very low frequency radio astronomy from the ground, which is an awful lot cheaper than doing it from space. There's the other one technical issue. These projectors that they use for this are 50 centimeters wide, and if it's going to be a long slit, then obviously the radiation is going to be polarized. But I mean, that's a fairly basic technical issue which shouldn't cause too many headaches if it can be done. So perhaps it could be done from Earth. If you can't do it from Earth, then obviously you've got to go out into space above the ionosphere here. That's the International Space Station, and obviously life gets more difficult. Now, the idea for doing this isn't just something that is proposed by fact, it's turned up in fiction as well. One of my favourite films, 2001, made in 1968, and in chapter 9 of that, he was played by Leonard Rossiter in the film, but Heywood Floyd goes up to the space station, meets this Russian and goes on to the moon. Well, in the book, this Russian astronomer that he talks to was tall, slender and blonde. Well, Leonard Rossiter was a good actor, but he was never like that. But anyway, that's the point here is this character had spent the last 10 years building up the giant radio observatory on the far side of the moon, where 2,000 miles of solid rock would shield it from the electronic racket of Earth. Now, we come back to the observatory on the moon. This was posted in 1985 because of terrestrial ionospheric absorption. Very little is known of the radio sky beyond 10 meters. The other problem, if you are going to do 10 meter or thereabouts radio astronomy from Earth, you get the best results when you can get them perpendicular to the Earth's surface. As you go off to the side, you're obviously going through more of the ionosphere, so the results deteriorate, and as you get a longer wavelength, the results get worse as well. They also get very patchy because of the ionospheric weather. So this is a summary of what Douglas and Harlan Smith said could be done in 1985. 2 lunar rovers, 3 crew, and the arrangement would be either a 15 kilometre square square of 10,000 elements. This would give a 1 degree beam. That's a lot better than the 5 degree that we saw on one of the earlier slides, or it could be done by a T-shaped array, 15 by 30 kilometres, again with 200,000 elements. Now the reason, this is maybe a bit of a red herring. A couple of years ago I was very privileged to have a visit of around the Mullard Radio Observatory outside Cambridge, and in the 70s when they were building the 1 mile telescope, they thought it had to be flat rather than following the curvature of the Earth. And cut a long story short, to make it flat, at the end of one end of the 1 mile telescope, it had to be propped up by 2 inches, so you had a perfectly flat thing, as opposed to Earth following the Earth's radius. The moon is smaller, so the curvature is a lot more. I did a quick calculation on the moon's diameter, 15 kilometres, it would be 64, 65 metres, but looking at the later proposals for lunar radio telescopes just laid out on the surface, they don't seem to bother with this at all. So maybe this is just a complete red herring. Now, as I said, I updated these slides last night. The original paper was written in 1985, and they're talking of 2 lunar rovers, 3 guys taking 1 month. Now, for ages, the International Space Station has been supplied by robotic spacecraft, and with the Alpha array during a 12-year mission, which is more or less 1 lunar cycle as well, based in the Chapligin crater, they should be able to cover 98% of the sky. So this is the later paper which I found two nights ago. This is from Harvard, and again it's more advanced than the 1985 paper, but it's also showing its age, because their scheme, which is about 20 pages, their scheme can be packed onto one Titan III rocket. Well, it would probably be cheaper to go to SpaceX and ask Elon Musk how many, probably $20, $30 million to put it on top of a SpaceX rocket. So even in the 7 years, there was a lot of progress on this. So that's the far side of the moon. For some reason, which we still don't know, seems to be more cratered than the side which faces us, and that's the Chapligin crater, which I believe is more or less there on the equator. Now, if you've got a technical problem, there's a saying, don't reinvent the wheel, or see what Mother Nature has achieved previously. Now, if you aren't going to put it on the moon, or maybe that's too expensive, one method might be, I'll mention this in the newsletter by the way, a floating array. I don't know how many kilometres across it would be. The parameter would be, the rule of thumb is that the spacing between the elements can't be more than 1/10 of the frequency concerned. But if you had a flat array, perhaps that could be set up as a phased array. Now there's a problem, of course. A spider affixes it to the window or plant or whatever in space, you ain't got anything to nail it to. And the only way I can think of, or the easiest way, is to have it rotating. This probably one of the flimsiest structures ever made. Have it rotating with weights here that would keep its flat shape. I don't think you'd have to worry about meteor impacts because they just go straight through it. But this would be, if this were flat, which would be the simplest arrangement, as a phased array, you could look at different parts of the sky at the same time. And you could also do with, again, if it's set up properly, you could run several surveys at once and get more bang for your buck. So a floating spider web in space, well, it's intriguing, interesting to see what the press would make of it. Probably the front page of the Daily Mail, but never mind. The other structure that springs to mind for this sort of thing is the jellyfish, where obviously you've got a curved thing. Now, I don't know how one would do that. Would one have ties, and then you've got to have the horn collecting the data at some point from there, rather like an umbrella if you hold it upside down. So that's another possible arrangement. Now, to keep it simple, assuming it's a spherical array rather than an elliptical one, you've got the principle, the radius of curvature, okay, that's for keeping its shape, but of course the focus for any signals is going to be half of that, which means that another gizmo or arrangement to actually collect the data. I do like, well, I just fascinate these jellyfish things floating in space. Now, one way you might keep the shape is maybe inflate it, and that is, of course, isn't a new idea. I'm old enough to remember Project Echo from 1960, well, Echo 1, Echo 2, 60 and 61, the world's first communication satellites. At that time, the first scheme for world communication satellites was drawn up. It was 3 reflecting balloons like this. It would have worked, actually, even with 1960s technology. The reason it's not being used now is that, of course, you couldn't get the data rates for a pure reflector. The whole point about satellite communications technology is the more data you can transmit, the more money you make, and this wouldn't have been any good for that. But anyway, the Echo satellite was set up to look at 2 areas of research. One is atmospheric drag at several hundred miles up. That data was incorporated into American spacecraft, and of course the pressure of the solar wind. Now what you got there is a big balloon. One of the more surprising things about it was this survived several meteorite attacks. This balloon, whatever plastic it was, had sprayed aluminium 11 microns thick. Now, aluminium is a metal. If you stretch it to just beyond the elasticity point, and there's a loss of tension, it will not shrink back. It will stay there. So somebody was very clever there. So even though this thing, so it kept its shape, even with several meteorite attacks. It burned up in 1968, I think, due to pressure from the solar wind, pushed it lower and lower into the atmosphere. But to keep the structural shape of any of these, the jellyfish or spiderweb arrays, we could use previous experience with Project Echo. Now, okay, so there might be this arrangement or that arrangement. Where would you put it? Well, one place you really wouldn't want to put it is near the Van Allen radio belts. This, caused by the Earth's magnetic field, enable life as we know it to exist on Earth. If they weren't there and we had life, we'd probably be, most of us would get skin cancer and wouldn't last very long. So these are rather nasty places. You really wouldn't want to put a telescope in space trying to pick up very low frequency, very weak radio signals. Now, one obvious place is Lagrangian points. These were discovered back in the 17th and the 18th century, just points in orbits where gravitational forces cancel out. There's 5 of them, and that's another version of them. Now, one interesting discovery from the research from this talk is most people understand that if you have a mass in space, you can put a satellite or something in orbit around it. Okay, everybody knows that. What I didn't realize is with there's something called a halo orbit. Now, at these points where the gravitational forces cancel out, there's nothing there. It's a point in space, but you are actually able to put something into orbit around that. This is done for some solar satellites. For example, if you're good at maths, this is something in the three-body problem of orbital mechanics. And the curious thing is, it's a point in empty space, but it can be orbited. One of the bonuses of doing the research for this talk. That's from Wikipedia, by the way. Related to halo orbits are Leicester orbits. Another bonus from the research. That's the top view and the side view for a satellite going into a Leicester orbit. One problem with these is it's in the mass. These are unstable and they need adjusted. And whereas the arrangements I mentioned so far would drift in space, which means you can't control them, but the point is it's an awful lot simpler and lighter than a satellite where you have to carry a load of fuel, and once the fuel has run out, then the satellite is pretty useless. On a sort of typical communications satellite, for example, that might weigh 6 tons. Half of that weight is fuel. The design life is 15 years, but once the fuel is used up, well, it's a bit of space junk. Now we're coming to the area which has been mentioned before in the magazine, and all of you who've come back to me and said, no, George, sorry, it won't work because, not what I wanted to hear, but I do appreciate the time that you've all taken to come back to me on the news group. And what we have here are two regular platonic shapes, the tetrahedron with 4 sides and the octahedron with 8 sides. Now, how would it work? Well, the satellites would be at the points, the vertices. Between each satellite would be a laser beam. The laser beam would be the antenna element. You would have a plane, and you could have 4 planes. And as a phased array, you could have it looking that way maybe, but with 4 faces in 4 different directions, you could cover the whole sky. Now, these would drift, as I said. With drifting, the sides would inevitably become different, but that can easily be corrected. That is basically like the same principle as tuning an antenna. I don't know how sensitive it would be, but the point is, with really long antenna elements, you could actually get some decent resolution on each face. So you have a satellite here, here and here. Between them, instead of a bit of wire, it would be an antenna beam. From the research I did earlier, the longest wire-guided missiles and wire-guided torpedoes, I think, are to about 5 miles. But of course, then there's the issue, well, supposing it breaks, it's pretty useless, which is why I had the idea of using lasers as the antenna elements. And the main question, will lasers work as an antenna element? Now, I've had conflicting advice here, and that's why I'm particularly grateful for you, John, for letting me talk. The advice from the newsletter on the Yahoo group is, sorry, George, it won't work. But as I said, I am doing an Open University degree in maths and physics, and I put this idea, basically, could a laser beam work as an antenna element? Am I being completely stupid here? And bit to my surprise, that the man who's in the physics department at OU said, no, it's not a stupid idea at all. He is actually, the man who gave me that advice a few months ago, he is actually working on LOFAR. He is doing a PhD into, I forget what it is, but he's got a whole mountain of data, and he's writing lines and lines of Python code to extract whatever lesson is there. What he did say is that there's something called forced damping is a relevant issue here. And where did George get the idea from? I'll be quite honest, it was from LIGO, the Laser Interferometry Gravitational Observatory, which apparently did detect gravitational waves back in 2015 when two black holes or two galaxies collided. That's the schematic representation of the two in the previous photo, and these are ones which are either under construction or are planned. What this shows, it's a triangle, the LISA observatory, the Laser Interferometry Space Array. This is 3 satellites, like one face of the array I mentioned. Each line would be 5 million kilometers long, and they would rotate around a Lagrangian point. But of course the lasers are being used as very accurate measuring rods rather than as elements for picking up radio signals. So I'm sorry I can't show you that. So what are the advantages of my platonic solids floating in space? Well, the LISA observatory, the elements are 5 million kilometers long. I don't know, mine would have to be that long, but with a longer element you could certainly get better detail. And one thing I found, again, from reading this book, and you guys in radio probably know a lot more than I do, where the antenna is much shorter than the wavelength, it's not very sensitive, and you don't get very good resolution. But again, get more bang for your buck. If you set it up properly as a phased array, you can run the surveys on several frequencies at the same time. Data, I didn't just mention this because it's interesting. One of the reasons why Project ELF didn't work was, firstly, it's incredibly inefficient. I haven't, 8 as a percentage of 2.6 million, I haven't even bothered to work it out. But the difference in data at these low frequencies is pretty mind-blowing. I mean, the square kilometre array, when it's up and running, is going to generate 10 to 20,000 petabytes a day, buckets and buckets of data. The scheme, when it ran 76 hertz, one reason why it was pretty useless, and the Americans only ever used it as a backup system, apparently it took 15 minutes to transmit 3 codes of letter. I mean, pretty useless, really. But I would hope to get a bit more data than that. I mean, at that sort of frequency, the idea of having a year's data on an old floppy disk is quite amusing, but I think we need something, need a bit more data than that to do something useful. So a friend at the physics department at the OU said, yes, it could work. No, it is not a stupid idea. He mentions LISA. And I've tried to paraphrase, rather read you the whole email, going back to ultra basics here on radio. Radio waves come in, they excite the electrons in an antenna, then they have to be tuned to the electronics and so on. Force damping is an issue. That's quoted verbatim, but what he means is where you might get an oscillation in the antenna at the wavelengths we're looking at, would that work with the frequencies in the electronics concerned? He talks about general radio frequencies, and VLF are hardly general radio frequencies. He also mentions that quantum mechanics, again, an area beyond my pay grade, if you like, that is relevant. What I'm talking about is apparently used in radio astronomy in mesas. Is there a suitable transition of the frequencies that we want to look at that will drive the electronic circuit? So to summarize the main issue of this whole talk, the problem is not the physics, the problem is the electronics. And okay, I've got my full radio amateur license, but I'm not active. But my electronics knowledge is pretty basic, but I know a lot of you here have pretty good electronic knowledge. But the issue is electronics, not the physics. So again, I'm really grateful to have the chance to be here. The areas where I need help are the antenna design. This is we're talking of very unusual antennas, electronic circuits design, as I just mentioned, laser technology as well. I wouldn't be surprised if it ends up being all three. And in case any of you think, George, I'm sorry, George, you're completely bonkers, or the idea is good, my answer, or not so much my answer, let me quote the great man himself, one of his lesser known sayings: unless an idea is dismissed as outrageous at the start, it has no chance to success. So thank you very much, Albert, and thank you all for listening.